I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about reflection and transmission of waves at boundaries, and also we'll be discussing the harmonic waves. Now if we look at the outline of this module, in the last class we have discussed transverse and longitudinal waves, and we have derived equations, wave equations for longitudinal as well as transverse waves. And today we are going to discuss about reflection and transmission of waves and harmonic waves. So how we are going to go about this topic? First, we'll be deriving the expressions for reflection and transmission coefficients. We'll understand how the phenomenon of reflection and transmission occurs in a wave, and with the help of the equations, we are going to derive expression for reflection coefficient as well as transmission coefficient. Then we'll also derive expressions for frequencies of harmonic waves. We'll first understand what are harmonics and then derive expressions for frequencies. And also, we will also discuss the laws of stretched strings, which will be very helpful to calculate the frequencies. So, this is how we are going to discuss this topic today. Now, let us start with a string. Okay, we'll suppose a string which consists of two sections and smoothly joined at the point x is equal to O with a tension T. So we will consider this is the string. Two sections we consider and they are joined here at the point. I can say this is the point of joint with a tension T. Now it can be considered as a part of the incident wave is reflected and a part of it is transmitted at the boundary x is equal to 0. So now what we consider is, if we have an incident wave, here at the boundary what happens, a part of it is reflected like this and a part of it is transmitted at the boundary. So what we are seeing is a reflected wave and also a transmitted wave at the boundary x is equal to 0. Now, the impedance on the reflected wave is denoted by Z1 and Z1 is equal to mu1 V1. So, here Z represents the impedance and Z1 we are denoting for reflected wave, and mu1 multiplied by V1. V1 represents the velocity of the reflected wave. Then comes the impedance of transmitted wave. So, for transmitted wave, we are denoting it by Z2, which is equal to mu2 V2. So, with this, we will try to derive the expressions. So, now we are considering the wave traveling along the positive x direction. So, the particle displacement of the incident wave is represented by the equation yi of xt is equal to ai sine omega t minus k1x. Since this is the first equation we are writing, we will discuss all the terms and the rest of the things will go with the same notation. So when I am writing y always represents the displacement. Y suffix I denotes the displacement of the incident wave. And xt here denotes y is varying with displacement as well as time. So x and t are the variables here. So we are talking about the displacement of the incident wave, which is given by ai. Again, a here represents the amplitude. A is the amplitude, that is the maximum displacement from the mean position. A suffix I is representing for the incident wave, sine omega t minus k1x. What is omega? Omega is the angular frequency, which is given by 2 pi upon t. And k1 here is the wave vector for the incident wave. So we consider k1 is equal to 2 pi by lambda. So we are calling this as equation 1. The first equation we are writing for displacement for the incident wave. So ai sine omega t minus k1x. Ai is the amplitude of the incident wave and the propagation vectors are given by k1 is equal to 2 pi by lambda 1. And for lambda 1, we can substitute nu upon v1 because v is equal to nu lambda. So if we want 1 by lambda, that will be nu upon v, where nu denotes the frequency and v represents the velocity. So what we are doing here, we are replacing this lambda 1 with nu upon v1 from this expression. Now the wave is reflected as well as transmitted at the boundary x is equal to 0. So this is the boundary x is equal to 0. What we are considering at the boundary, a part of it is reflected and a part of it is transmitted. So the reflected and the transmitted waves can be expressed as. So how are we denoting the reflected wave? So the reflected wave is given by YR xt. Xt here again the variables. YR denotes the displacement in case of a reflected wave is equal to AR sine omega t plus k1x. So if you see here, for the incident wave, we have taken it as AI sine omega t minus k1x. Here what we are doing, we are taking the reflected wave and these two are opposite in direction. So the reflected wave is going along the negative x-axis. So we have omega t minus of minus k1. So we get omega t plus k1x. So this gives the expression for the reflected wave. Let us take this as equation 2. Now, the equation for transmitted wave. So, this is the transmitted wave yt. T, the suffix t represents the transmitted wave. As a function of xt gives us at sine omega t minus k2x. So, why minus k2? Because the transmitted wave is going along the positive x-axis, just the same way in the direction of the incident wave. If you see the directions of the incident wave and the transmitted wave, they are the same. So we are considering omega 2 minus k2. K2 because it is going into the as a transmitted wave, maybe a different medium. So the wave vector may vary. So yt of xt is equal to at sine omega t minus k2x. So let us take this as equation 3. Now here AR and AT are the reflected and transmitted amplitude. A always represents the amplitude, AR represents for reflected wave and AT represents the transmitted wave, amplitude of the transmitted wave. And K2 will be equal to 2 pi by lambda 2. That will be 2 pi nu upon V2. So it is coming from our general formula. What we have is, we have already seen V is equal to nu lambda. So 1 by lambda will be equal to nu upon V. So we are writing for lambda 2. So it will become a V2. So 2 pi by lambda 2 will be equal to 2 pi nu upon V2. Now let us see the boundary conditions. What are the boundary conditions on this waves? So the first condition is y of xt is continuous across the boundary at x is equal to 0. So y of xt means the displacement is continuous across the boundary. So therefore, dou y by dou x is also continuous. When you take the derivative, and we are considering the partial derivative here because we have two variables, x and t. So when we are doing with respect to x, we keep t constant. So dou y by dou x is also continuous. That will be the first boundary condition. Now coming to the second boundary condition, the transverse component of tension is continuous. So y of xt is continuous and the transverse component of tension. What is the transverse component of tension? We are taking here as minus t dou y by dou x of xt is continuous at x is equal to 0. So we are going to apply these two conditions for the waves now. So at boundaries, what we are considering is the incident wave is represented by AI sin omega t, reflected wave by AR sin omega t, and the transmitted wave by AT sin omega t. Now we'll apply the first boundary condition. So what we have here is AI sin omega t plus AR sin omega t should be equal to AT sin omega t. At the boundary, if you see, AI sin omega t plus AR sin omega t should be equal to AT sin omega t. So sin omega t is common here. So if I take out sin omega t, I have AI plus AR will be equal to AT sin omega t. So sin omega t gets cancelled on both the sides. What we are left with is AI plus AR is equal to AT, and this is equation 4. This is what we are getting by applying the first boundary condition, AI plus AR is equal to AT. Now we will consider equations 1, 2 and 3, where we have seen the displacements for the incident wave, reflected wave as well as the transmitted wave. So what is the first equation? yi of xt is equal to AI sin omega t minus x1 k1x. So if we are applying it for this, what do we get? Dou yi by dou x of t is equal to minus AI k1 cos omega t minus k1x. Because when you are taking the partial derivative for this, so what do we get here? We are keeping t constant, so the derivative with respect to x. And for sin omega t minus kx, we have for dou yi by dou x, ai. For sin, we have cos omega t minus k1x. And for k1x, we get minus k1. Omega t remains constant here. So we get minus k1. So minus ai k1 cos omega t minus k1x. That is what we have got. Now for a reflected wave, we have the equation yr of xt is equal to ar sin omega t plus k1x. So what will be dou yr by dou x? So dou yr by dou x will be ar k1 cos omega t plus k1x. The same rule we will apply here. We are keeping the time constant and we are taking the partial derivative with respect to x. So for sin omega t plus k1x, we get cos omega t plus k1x. And for k1x, we get k1. So what we are getting here is ar k1 cos omega t plus k1x. So this is what we get from equation 2. Now what is our equation 3? For the transmitted wave. So yt of xt is equal to at sin omega t minus k2x. So the derivative, the partial derivative dou yt by dou x will be minus at k2 cos omega t minus k2x. So that is how we are finding dou yi by dou x, dou yr by dou x and dou yt by dou x for all the three waves, the incident, the reflected and the transmitted waves. Now at the boundary, x is equal to 0. This is the condition. So how the expressions are going to get modified? So in this expression, dou yi by dou x this is what we got now, minus ai k1 cos omega t minus k1x. So if x is equal to 0, this equation or this term goes to 0. So what are we left with now is minus ai k1 cos omega t, because this term goes to 0. So what is it for the reflected wave? Again, this is the equation where this goes to 0. So we have AR K1 cos omega t. AR K1 cos omega t. And for transmitted wave, again this goes to 0. So we have minus ATK2 cos omega t. So these are the equations after applying this condition, that is at the boundary x is equal to 0. So now we will take forward these three equations and we will apply the second boundary condition. What is the second boundary condition? Minus t dou y by dou x is continuous at x is equal to 0. This is the second boundary condition. The transverse component of the tension is continuous at x is equal to 0. So now we will try to apply this second boundary condition. So what is the equation we have? Dou yi by dou x, xt is equal to minus ai k1 cos omega t after we have applied at x is equal to 0. So what we get here for all the three equations we are going to write. This is for the incident wave, for the reflected and for the transmitted. For all the three, we are going to apply the second boundary condition. So minus t into dou y by dou x. So when you have minus t into this, we get TAI K1. So this will give us TAI K1. Of course, the cos omega t is there. And here we get minus t AR K1 cos omega t. And for the transmitted wave, we get minus t, minus into minus, so we get plus t ATK2 cos omega t. And because it is continuous, what we have is TAI K1 cos omega t minus T AR K1 cos omega t will be equal to TA TK2 cos omega t. So this is the equation we are getting now. So we will have, after applying the second boundary condition, what we have got is this equation. Now here we are going to take out cos omega t common. So cos omega t is common. So I can write it as cos omega t into T AI K1 minus T AR K1 is equal to T AT K2 cos omega t. So cos omega t will get cancelled. And in both the cases here we have K1t and K1t. We have taken now K1t common. So we are left with AI minus AR. So K1t into AI minus AR will be equal to K2t into AT. So we will consider this as equation 5. So we are going to substitute in this equation next. So all the terms we know now. What is K1t? We know K1 is 2 pi by lambda 1. We have already seen in the first few slides. 2 pi by lambda 1 into t. And we have also substituted for lambda 1 as nu by V1. So for K1t, we can write 2 pi nu by V1 into t. And what is this 2 pi nu by V1 into for t? We can substitute V1 square mu 1. So how we are getting it is from this expression V is equal to under root T by mu. We have derived the expression for the velocity of a transverse wave. Yesterday we have seen the complete derivation for this. So V is equal to under root T by mu. So when I do the squaring on both sides, we get V square is equal to T by mu. And if we want T will be equal to V square mu. So in place of T here, we are substituting V1 square mu 1. So 1 V1 and 1 V1 will get cancelled. So we will be left with 2 pi nu V1 mu. So what is K1t will be equal to now? 2 pi nu V1 mu1 after substituting for K1 as well as T and simplifying we are getting 2 pi nu V1 mu1 that will be equal to 2 pi nu Z1. Z1 here represents the impedance for the reflected wave. What is impedance given by Z1 is equal to mu1 V1. So we have substituted for V1 mu1 Z1. Okay. Now what is K2T? So K2T will be on similar lines 2 pi nu V2 mu2. And for V2 mu2 we are going to substitute Z2 because the Z2 here is the impedance of the transmitted wave. So Z2 is equal to mu2 V2. So for mu2 V2 we have substituted Z2. So we will consider these two equations now as equation 6 and equation 7. So K1t is equal to 2 pi nu Z1. K2t is equal to 2 pi nu Z. Now substituting these two equations 6 and 7 in equation 5. What is our equation 5 we got? K1t into AI minus AR is equal to K2t into AT. This was our equation 5. So substitute these two values for K1t and K2t in this equation. So what we get is for K1t I am substituting 2 pi nu Z1. So 2 pi nu Z1 into AI minus AR. This is on the left hand side. This will be equal to, for K2t, we are substituting 2 pi nu Z2. So this will be 2 pi nu Z2 into AT. So 2 pi nu Z1 into AI minus AR is equal to 2 pi nu Z2 into AT. So let us take out the things, strike off the things which are common. Here 2 pi nu and 2 pi nu are common on both the sides. So we write it as Z1 into AI minus AR is equal to Z2 into AT. Let us consider this as equation 8. So this is very important now. Z1 into AI minus AR is equal to Z2 into AT. Now substituting the value of AT from equation 4. What is our equation 4? AI plus AR is equal to AT. So for AT, we are going to substitute AI plus AR in equation 8. So we'll take equation 8. This is our equation 8. This was our equation 4. So from 4, we are going to substitute for AT. AT, AI plus AR, we are going to substitute AT. So here, for AT, we will put AI plus AR. So what will be the equation now? The left hand side remains the same. Z1 into AI minus AR. So Z1 into AI minus AR is equal to Z2 into, for AT, what we are substituting? AI plus AR. So we are getting here AI plus AR. So on substituting the value of AT from equation 4 in equation 8. So now let us rearrange these terms and write. We have AI on the left hand side and AI on the right hand side also. So we will bring both onto this side. So we have AI Z1 and minus AI Z2. So AI into Z1 minus Z2 will be equal to AR. Here we have Z2. And if you bring this AR Z1 onto this side, it will become plus Z1. So AI into Z1 minus Z2 will be equal to AR into Z2 plus Z1. So now we are going to write the ratio of the reflected wave to the transmitted wave. So we want AR upon AI. So we'll take Z2 plus Z1 onto the other side. So it is Z1 minus Z2 upon Z1 plus Z2. So this AR upon AI is called the reflection coefficient. So AR upon AI is known as the reflection amplitude coefficient, and it is also represented by R12. So it depends upon the impedance of the two, the reflected wave as well as the transmitted wave. So we have got the reflection coefficient. Now let us see the transmission coefficient. So from equation 4, we will write AR is equal to AT minus AI. So what was our equation 4? AI plus AR is equal to AT. So from there we have written AR is equal to AT minus AI. And we are going to substitute this value in equation 8. So this is our equation 8. So where did we get this from? AI plus AR is equal to AT. This was our equation 4. So from here what we are writing, AR is equal to AT minus AR. We are going to substitute this value of AR here because we are going to now find the transmission amplitude coefficient. So we are trying to eliminate the amplitude of the reflected wave. So we are substituting for AR. So when you substitute, what you get, Z1 into AI minus AT minus AI. So for AR, we are going to substitute AT minus AI. And the right hand side remains the same, Z2 into AT. So this remains the same. Now let us simplify. So we have Z1, this is AI minus AT, and minus of minus is again plus AI. So AI plus AI, we get 2AI. So Z1 into 2AI minus AT will be equal to Z2 into AT. So this implies 2Z1 AI. Here we are multiplying with Z1. 2Z1 AI minus Z1 AT will be equal to Z2 into AT. So we will be taking this transmission coefficient also onto the other side. 2Z1 AI is equal to Z2 AT plus Z1 AT. Because this, when it comes on to the right hand side, it will become plus Z1 AT. So we are writing 2Z1 AI plus Z1 AT plus Z2 AT. So now you can take out AT common here, AT. So Z1 plus Z2. Here we have Z1 and Z2 after taking out AT common. Now we are going to write for AT upon AI. So AT upon AI, if we have 2Z1 here, and we are going to take Z1 plus Z2 onto the other side. So what we have is 2Z1 by Z1 plus Z2. So AT by AI here represents the transmission amplitude coefficient. And we'll consider this as equation number 10. So the transmission amplitude coefficient is represented by T12. Reflection amplitude coefficient, we were denoting it by R12, and the transmission amplitude coefficient is represented by T12. So with the help of these two expressions, AT by AI and AR by AI, we can calculate the transmission as well as reflection amplitude coefficients. Now let us move on to see about the waves on string. How the waves or the harmonics are developed on a string. So now, if you consider a string which is stretched at both the ends and it is brought into oscillations. So I have taken a string here, a string which is fixed at both the ends. So if you just pluck it from here and leave it, it starts oscillating. No? So when it is brought into an oscillation, it forms a vibrating string. So in our day-to-day life, we see many vibrating strings. The best example is the violin string. So the strings in a violin. What happens here? When you just pluck the strings and leave, these strings will vibrate back and forth between the ends. So the strings of the violin or the guitar, any musical instrument, stringed instrument you take, there are strings which are fixed at both the ends. So when they are fixed at both the ends and when you just pluck the strings and leave, they keep on oscillating. So you call them as vibrating strings. Now, the waveforms that appear when these strings vibrate, they appear to be stationary. But in reality, they are not. They are called standing waves. There are waves, but they are standing waves. So what are standing waves? They are produced due to superposition of two identical waves. Identical here means identical in amplitude and frequency. Amplitude here denotes the maximum displacement. When I am considering two waves that are superimposing on each other, these two waves should be identical. Means they should have the same amplitude and also the same frequency. And we call them as progressive waves when they are moving forward. And these two waves when they are traveling along the same line but opposite in direction. So the waves that are having the same amplitude and frequency traveling along the same line but in opposite direction, when they superimpose on each other, you get standing waves. So you see here for this wave, this is the wave which is going in the forward direction. And it is reflected back from here, it is coming in the opposite direction. So these are the two waves. I can say this wave may continue forward if this obstacle is not there. So here the amplitude is the same for both. The frequency is also the same. They are traveling in opposite direction along the same line. Then what we get is standing waves. Now, standing waves which appear to be vibrating vertically but without traveling horizontally. So they just vibrate about the mean position. The particles of the medium vibrate and you have standing waves, but the wave is not proceeding forward in the horizontal direction. Then in a standing wave, what we see are nodes. What are nodes? They are the positions where the resultant displacement is zero. Why we are talking in terms of resultant displacement? Here we are having two waves which are traveling in the opposite direction. Of course, they are of the same amplitude and frequency. So the positions where the resultant displacement is zero, we call them as nodes. And antinodes are positions where the resultant displacement is maximum. Where the displacement is maximum, you call them as antinodes. Where the displacement is zero, we call them as nodes. So now let us see in this figure. We will consider the first wave like this. Or you can take it in the other direction also because this is coming, maybe it may get reflected. So I will take it in this direction. Now there are some points here. At these points, the displacement is minimum or zero. And such positions we call them as nodes. And there are regions where the displacement is maximum. So all these correspond to antinodes. So if you see a stationary wave or a standing wave, you will see a series of nodes and antinodes. So this is a node, antinode, node, antinode, node, antinode, and so on. So it consists of a series of nodes and antinodes which alternate each other. Now, the distance between two successive nodes or two successive antinodes is equal to half the wavelength. So let us try to understand that. Now we will consider two nodes. This is one node and this is one node. And this is the third node. We will consider the distance between these two nodes. It is given by lambda by 2. The distance between any two nodes. You can take antinodes also. I may take from here to here. This is also lambda by 2. So the distance between any two nodes or antinodes is equal to lambda by 2. Why lambda by 2? Because we know this is one complete wave. This is one complete wave. And when we are talking about two nodes, this is half of the wave. So it is lambda by 2. For one complete wave, the wavelength is given by lambda. So for half the wave, we consider the wavelength as lambda by 2. Now between a node and an antinode, what is the distance between a node and an antinode? So we consider this is the antinode and this is the node. So what will be the distance between that given by lambda by 4? Why again the same thing we see here, because this is a complete wavelength, lambda for a complete wave. So this is only 1/4 of the wave. So it is lambda by 4. So what we try to understand here, lambda by 2 is the distance between any two nodes or any two antinodes. And lambda by 4 is the distance between a node and an antinode. So you see here, this is the node and node. So we are denoting for the complete wave, we are writing wavelength lambda. If I am taking this is the complete wave, and for a standing wave, you have in the other direction. This is the complete wave whose wavelength is given by lambda. Now if I take between node and node, it is only half of the wave. So this will be lambda by 2. Now if I take between a node and an antinode, this is half of half. So this will be lambda by 4. So between two nodes, it is lambda by 2. And between a node and an antinode, it is lambda by 4. Now let us understand and differentiate between progressive waves and stationary waves. So what are progressive waves? They are produced due to continuous vibrations of the particles in the medium. And here stationary waves are produced due to superposition of two identical progressive waves. Identical here means same frequency and amplitude. They are moving along the same line but opposite in direction. Progressive waves means they move forward into the medium. Particles of the medium vibrate continuously. But in case of stationary waves, the wave does not proceed forward. It is reflected back. And what we have here is a stationary wave. And the second point, the waves move forward continuously with finite velocity and transmits energy. So the energy is carried forward in a progressive wave. But here in a stationary wave, there is no advancement of the wave. It is limited to a certain region. And so it does not transmit energy. Or I can say the energy is limited to that particular region. And the third point here is each particle of the medium executes identical periodic motion about the mean position of rest. And the phase of vibration varies continuously from point to point. So the motion is periodic and it is about the mean position. And the phase varies continuously. Phase here tells about the state of vibration of the particle. And it is going to vary continuously from point to point. But if you see in a stationary wave, particles between two successive nodes are in the same phase. Two successive nodes you take and compare the vibrations of the particles, they will be in the same phase. And while particles in opposite side of the node are in opposite phase of vibration. So on the opposite side, they are in a different phase. So on the same side, they are in the same phase. Now the amplitude of all the particles is the same in case of progressive waves. But here, the amplitude varies continuously from point to point. So how it is varying? At the nodes, it is maximum. And at the nodes, it is minimum. And at the antinodes, it is maximum. So maximum at antinodes and minimum at nodes. That is how the amplitude keeps on varying. So this is how we differentiate, compare and contrast progressive waves with stationary waves. Now let us see harmonic waves. What are harmonics? Harmonics are groups of frequencies that produce higher notes. So when you are talking about a frequency, which is producing higher notes, then that group we call them as harmonics. So a harmonic wave displacement is given by y of xt is equal to a sine kx minus omega t plus phi. So the same way we see the displacement, y of xt is equal to a sine kx minus omega t plus phi. Suppose in case the initial phase phi is equal to 0. Phi here denotes the initial phase. So in case the initial phase is 0, we simply write y is equal to a sine kx minus omega t. This is what we have been considering till now. Considering that the particle starts from the mean position. And k here again is the wave vector which is denoted by 2 pi by lambda. And omega is 2 pi by t. Omega is the angular frequency which is denoted by 2 pi by t. And v is the velocity. How velocity, frequency and wavelength are related? V is equal to f lambda and phi represents the phase angle. Now from the figure we will try to understand how higher harmonics are formed. So each loop is 1/2 of the wavelength. Now we have already discussed the first loop, that is if we have a string of length L and you just pluck it and leave it. In the fundamental mode of vibration, it will vibrate with one loop like this. This is called the fundamental frequency. I call it as fundamental mode of vibration or the first mode of vibration. So in the first mode of vibration, what we have? We always have a node at the fixed end. So here also there is a node. So there is one single loop. So what we see here, when the entire length of the rope accommodates only one loop, then we call it as the fundamental frequency, and that is the lowest possible frequency. So this is the lowest. You cannot have a string with half of this, means you cannot have an antinode here and a node here, because always at the fixed ends we have nodes. So this is the least possible vibration. So we call it as the fundamental frequency. Now the next mode of vibration. So definitely there are nodes at both the ends and there is one more node at the center. So now it consists of two loops. So this will be the second harmonic. This forms the second harmonic. So in this case, what we have seen is, this is L. So L here will be equal to, I will write capital L is lambda by 2. No, because the distance between any two nodes is given by lambda by 2. And in the second harmonic, what we are having is two loops. So we have the distance between any two nodes is lambda by 2. And this is also lambda by 2. So L here is given by lambda. Now in the third harmonic, we'll have three loops. So in three loops, what we have? This is lambda by 2. This is lambda by 2. Lambda by 2. And again lambda by 2. So how many lambda by 2s we have? 3 lambda by 2. Now in the fourth harmonic, we will have 4 loops. So that will give us 2 lambda or 4 lambda by 4. So the subsequent 2 loop, 3 loop, 4 loop, they are called the second, third and fourth harmonics. So you understand what are harmonics? They are nothing but group of frequencies. So here we are seeing the fundamental, the second harmonic, third harmonic, fourth harmonic and so on. Now fundamental frequency, it is the lowest frequency of a standing wave that has the fewest number of nodes and antinodes. So what we have here in this is, we had 2 nodes and 1 antinode. As I told you, always we have a node at the fixed end. So we have 2 nodes and 1 antinode. Now a harmonic here, when we are talking about a standing wave, that is a positive integer multiple of fundamental frequency. So always when we are talking about harmonics, harmonics are always integral multiples of fundamental frequency. That is what we are going to understand in the next slide. For all standing frequencies, the nodes and antinodes alternate with equal spacing. This also we have discussed. The distance between any two nodes or antinodes is fixed and they are equally spaced. So each harmonic results in additional node. So as the number of waves increases, so the number of nodes also increases. So an additional half of the wave is introduced within the string. So for each harmonic, half the wavelength is being introduced. So now let us try to write. If the number of waves in the string is known, then an equation relating the wavelength of the standing wave pattern can be algebraically derived. We can derive the expression. So what we are doing now for the first harmonic, let us call it as the fundamental frequency F1. And what is the length given by? Lambda by 2. Because why lambda by 2? It is the distance between two nodes which is given by lambda by 2. So here for the first harmonic, I'll call it as lambda 1. So for the first case, L will be equal to 1 loop 1 into lambda 1 by 2. Now for the second case, we have two loops and each loop is of lambda by 2. Because it is a second harmonic, I'll denote it with lambda 2. So we have 2 into lambda 2 by 2 for the second case. That is where we have two loops or the second harmonic. And for the third harmonic, we have 3 loops. So we are writing 3 into lambda 3 by 2. And so on we can continue. So as the number of loops increases, so the number here increases, the value of n increases. So I can generalize it and write it as capital L will be equal to n into lambda n by 2. So if there are 10 loops, it will be 10 into lambda 10 by 2. So this will be the general expression. Now we can write the value of lambda n from here when L is equal to n into lambda n by 2. So this implies lambda n will be equal to 2L upon n. We are simply taking 2 onto the other side and n will come to the denominator. So lambda n is equal to 2L upon n. Now how do we write the expression for frequency? If V represents the velocity and F is the frequency, lambda is the wavelength and n is the number of loops, we have just now derived this expression lambda n is equal to 2L upon n. So what will be our velocity? We know V is equal to F lambda or n lambda. I am not writing n lambda because n we are denoting the number of loops. So V is equal to Fn into lambda n. So we are denoting the frequency by F. So if I have to write the formula for Fn, Fn will be equal to V upon lambda n. Fn is equal to V upon lambda n. And now for lambda n, we are going to substitute 2L by n. So this will be equal to V into n upon 2L. Because 2L by n is in the denominator. When it comes V into n by 2L. And Fn will be equal to, I write n by 2L into V. For V, what we are substituting here is under root T by mu. This is what we have derived for a transverse wave. So first we have substituted for lambda n here. 1 by lambda n will be n by 2L. And then for V, we are substituting under root T by 2. So the expression to calculate the frequency is n by 2L under root T by mu. So with the help of this, we are going to define the laws of stretched strings. So if you have to write the laws of stretched strings, the first one is the law of mass. So what the law of mass says is, for a string of constant length and uniform density, the density means it should be a uniform wire, okay, whose density is uniform throughout and it is under constant tension. We are plugging the two ends to fixed supports so that there is some tension in the string. Then the frequency of vibration is inversely proportional to the square root of mass per unit length. So F is proportional to 1 upon root mu. What is mu here? Mu is the mass per unit length. the total mass of the string divided by total length of the string will give us the mass per unit length. This is called mass per unit length. So F is proportional to 1 upon root mu. Now the second law is the law of length. So what is law of length? For a string under constant tension, the frequency is inversely proportional to the length of the string. So F is inversely proportional to L. F is proportional to 1 upon L, we write, or inversely proportional to L. So the second law is related to the length of the wire. Means what? If the length of the wire increases, the frequency decreases. That is what we mean by inversely proportional. And the converse is also true. If the length decreases, the frequency of vibration increases. Now, the third law is the law of tension. So, for a string of constant length and uniform density, the frequency of vibration is directly proportional to the square root of tension. So, F is directly proportional to root T. So, this is the third law. Now, we are going to combine all the three laws. What is the first law? F is proportional to 1 upon root mu, or inversely proportional to the square root of mass per unit length. The second law is the law of length. Frequency is inversely proportional to the length. And the third law is the law of tension. It is inversely proportional. Here frequency is directly proportional to the square root of tension. So now I am going to combine all the three and write it as F is proportional to 1 by L under root T by mu. We can remove the proportionality sign and we put a constant. So the frequency of the stretched strings is given by F is equal to 1 by 2L under root T by mu. This is the general expression for any stretched string to find the frequency. So for more details regarding this topic on harmonics, you can refer to Engineering Physics by Harbola, Vijay, Krishna and Madhumohan by Cengage Publications, or you can also refer to Gaur and Gupta Engineering Physics. Thank you and see you again in the next class.
Like, share and subscribe. Hit the bell icon for more updates.